Believe it or not, we have made it through the first third of the semester, and we are moving on to a brand new topic today to start the second third of the semester. And the second third of the semester is all about electric machines. That's where part of the name of this course comes from, electric circuits and machines. So we've talked about DC electric circuits in the first third of the class, and we're going to talk about electric machines in the second third of the class. And I have to tell you, I love all of this class. I really do. I love all of the sections of this class, but I really love this second third of the class because it's so important. Electric machines are just so important to our daily lives. We use them so much without even really thinking about them. So they really explain a lot of our way of life and how society works. It's so important to society. For example, the first types of machines that we're going to talk about in the next section are generators. We'll talk about different kinds of generators, but basically generators are producing electricity for us, right? And electricity is what we put on the electric grid, and we use that so much without even thinking about it. I'm probably using half a dozen electric devices right now without really even thinking about it. Like my wristwatch and my phone and my laptop computer, my desktop computer, my monitor, the lighting system, the ventilation system is using electricity to provide heat for this building, to pump the hot air, to blow it throughout the building. So all those ways we're using electricity right now, and if you look around, you're probably using somewhere around half a dozen electric devices right now as well. That's about the first week or 2 weeks of this next section in the class. And then after that, it's not really much of a jump to go from generators to talking about motors. A motor is really just a generator operating in reverse. You know, a generator, you put kinetic energy in and you get electrical energy out. A motor, you put electrical energy in and you get kinetic rotating energy out. So they're really quite similar. And we use motors a lot as well. In fact, motors are kind of underappreciated, I think. About half of the electrical energy produced in the US is consumed by motors, electric motors, which is kind of strange to think about until you start thinking about all the ways that we use motors. Probably the biggest place where we use motors is in heating, ventilation, and air conditioning systems. For example, I'm using a motor right now because I'm sitting in my office and it has heat. And so there is a motor powering a blower, a fan, that is blowing hot air throughout this building, thankfully. So it's keeping me warm right now. I also use an electric motor on my way to work today because I have a hybrid vehicle. I also used a motor this morning because I used the refrigerator, and the refrigerator contains a motor that drives a compressor to drive the refrigeration cycle in the refrigerator. So that's important to our way of life, refrigeration is. Also overnight, I used a motor to drive the heating system in my home, because once again, there was a motor driving a fan or a blower that drives hot air throughout the ductwork in my homes. Also in the summertime, air conditioning systems use several motors. Air conditioning systems actually have 3 different motors. They have one motor that drives the fan in the air handling unit to drive the air throughout the ductwork in the house. They have another motor that drives the compressor to push the refrigerant around the refrigeration loop in the air conditioning system. And they have another motor that you see outside in the air conditioning unit outside your home. That's a big motor that drives a big fan that's kind of loud, and it's providing cooling through the coils to reject the hot air from the air conditioning system. So we use a lot of motors without even really thinking about it. And there's a lot of devices that actually do use motors. The unifying theme behind all of these devices, different kinds of generators and different kinds of motors, the unifying theme is that they use magnetic fields in a clever way. So that's actually the first thing we're going to talk about today is magnetic fields, what they look like and how we can use them. So the first lab in this section of the class is Lab 8, and that's what we're going to do today. And Lab 8 is really easy because I'm basically gonna do most of it for you. And you just kind of have to follow along and write down on your lab 8 what I write down on lab 8 right here as I'm doing it. So I'll probably leave a little bit at the end for you to do on your own by yourself, but for the most part, I'm pretty much going to do all of lab 8 or the vast majority of lab 8 for you. So you just get to watch and copy down what I'm writing down on my lab 8 paper. All right, so I'm excited to get started in this second third of the semester. So let's go ahead and talk about a brief outline of what we're going to talk about in this section of the class, and then let's get started talking about magnetism.
So if I were to make an outline of what we're going to be discussing over the next month to 6 weeks, it would look like this. Today we're going to start talking about magnetism and what it is, where it comes from, some of its effects. And then from there, we're going to talk about electromagnetism, which is how electricity and magnetism are related, and it turns out they are closely related. And then from there, we're going to talk about induced voltage, which is actually how you use magnetism to induce a voltage in a coil of wire, which is exactly what a generator is. So from there, we'll talk about AC generators, because they're actually a little bit simpler than DC generators. But from AC generators, we really only have to make a couple of slight modifications to talk about DC generators. And from DC generators, it's not that big of a leap to talk about DC motors, because really a DC motor is just a DC generator operating in reverse. If you think about it, a DC generator, you put in rotating kinetic energy. We'll talk more about this later, but with a generator, you put in rotating kinetic energy and you get electricity out. A motor is the exact opposite. A motor, you put electrical energy in and you get rotating kinetic energy out. So they're really not too dissimilar. So after we talk about DC motors, we'll talk about AC motors. And after we've talked about all of that, it's a pretty easy last step to talk about transformers. And that's where we're going to leave off and have the second exam. So that's what we're going to talk about over the next month to 6 weeks or so. So let's start today by talking about magnetism. And I'm going to go ahead and talk a little bit about magnetism here, just a couple of things, and then we're going to jump in and do the lab. So first of all, the first question that you might ask about magnetism is, where does it come from? And magnetism is caused by the alignment of subatomic particles. And if you had to guess, you could probably guess which subatomic particles. Which subatomic particles are responsible for electricity, generally speaking? It's the electrons. So specifically, it's the alignment of the electrons. And even more specifically, when we talk about the alignment of electrons, that's kind of a weird thing to think about, but what we really mean is something called electron spin, which might not be something that you've heard of before. So what electron spin means is that as the electrons are filling up the electron shells around the nucleus, each electron is said to either have up spin or down spin. And so this is kind of it's a helpful visualization or construct. You can think about an electron as a little sphere that's rotating on its axis around the nucleus, kind of like the Earth rotates on its axis around the sun, right? So that's kind of what you can think about, and that works. I feel like I should probably point out that that concept of an electron spinning on its axis around the nucleus is actually an outdated model of the atom. That's called the Bohr, B-O-H-R, model of the atom. And the most recent model of the atom is quantum mechanics. And quantum mechanics really has to do with more of an electron cloud and a probability density function of where you might find the electron at any point in time. So this idea of an electron rotating and spinning around the nucleus is a little bit outdated, but it actually works pretty well, and it's a pretty helpful construct. And so we talk about the electrons spinning, so you can kind of think of them either spinning in one direction or spinning in the other direction as they're spinning around the nucleus. And that's gonna work for us. We don't need to get into quantum mechanics, and this model works very well to explain all of the effects that we're going to talk about in this class. If you take an advanced physics class, you might get into quantum mechanics where you can talk about some more details of exactly how electrons operate and how they spin around the nucleus. But this is going to work really well for us. So really what I'm trying to say here is that as electrons are filling up the electron shells around the nucleus in the atom, normally they're going to be evenly matched between upspin and downspin. So if you have 8 electrons in an electron shell, 4 of them are going to have upspin and 4 of them are going to have downspin. And so they kind of cancel each other out. But what can happen sometimes in certain materials, or if you induce a magnetic field in a certain material, you can have more electrons with upspin than downspin, or vice versa. And when you have that, that's when you have a magnetic field around the material. All right, so that's where it comes from. That's all the level of detail that we need to get into for where does magnetism come from. Most of what we study is going to be the effects of magnetism. The other thing I want to say right now is that every magnet is a dipole. What is a dipole? A dipole means that it has 2 poles. The prefix di, di, means 2. So every magnet in the practical world, I'm not saying that you can't possibly make a monopole magnet in the laboratory, but every magnet in the real world is going to have 2 poles. So that means that every magnet has a north pole and a south pole. And a good question is, what if I took this magnet, this is a bar magnet with a north pole and a south pole, what would happen if I took this magnet and I broke it in half? Well, what would happen is now I've got 2 bar magnets, and each one has a north pole and a south pole. So this half would have a north pole and a south pole, and this one would have a north pole and a south pole. So in the real world, in practical applications, every single magnet has 1 north pole and 1 south pole. That's actually enough background for us to get started with the lab, and I'm going to go ahead and walk through the lab with you, and you go ahead and follow along and draw in basically what I draw in on the lab document. So first of all, we're supposed to lay this bar magnet on the page, right, like that. It fits just perfectly. And then we're going to use this small compass, and you can see the orientation of the needle of the compass, hopefully. And what we want to do is draw the path of the magnetic field. Now, first of all, I'm just going to rotate this compass around, and hopefully you can see that the needle of the compass is changing its orientation depending on where it is in relation to the compass. Can you see that the needle of the compass is changing its orientation based on where it is relative to the magnetic field? All right, so what I'm going to do here is I'm going to pick about 12 or 15 places around the bar magnet, and I want to draw the orientation of the needle of the compass. That's what I'm going to do. So right here, it looks like the needle is pointing approximately that direction. And right here, it's pointing approximately that direction. And here, it's pointing approximately that direction. Here, it's pointing that direction. Here, it's pointing that direction. All right, so that's pretty good. I don't know how many that is, but that's probably approximately 12, 15 different points. And then what we're going to do now, after we've got all of those, what we want to do is connect these. I want to connect these individual lines. And so what you would see, especially if you had even more of these, what you would see is that there's kind of a pattern. It kind of goes from one pole to the other pole. So we can kind of connect these. All right, kind of like that. Good. So what we've just drawn is the shape of the magnetic field around this bar magnet. So that's good for right now. We're actually not done with that. There's something else we need to add to this before we say we're done, but this is going to be good for right now. So let's move on to the next page. And that says to create a solenoid. And remember, we've talked a little bit about solenoids before. What we're going to do is we're going to wrap a long length of magnet wire into a coil with many turns. So I've got a long length of wire right here. This is called magnet wire. And magnet wire has a really thin coating of insulation around the outside of the wire. So when I wrap it into a coil, it's not just going to short itself out because there is insulation around the circumference of each section of the wire. So what we're going to do is we're going to take this long length of wire and we're going to wrap it into a coil. And what I found works pretty well is to wrap it around a marker. That's kind of a nice diameter. So I'm just going to start wrapping this wire in a coil around this marker. It's about half of the wire right there. I hope I can get this coil off of the marker. I have a feeling it's going to be difficult to get this off of the marker. Okay, that is all the wire. There we go. So now we got a coil of wire, and I hope I can get this off. All right, I got the coil of wire off of the marker, but that was actually pretty challenging. The next thing we're going to do is we're going to connect the leads of this coil to a power supply. And I've actually got a power supply. I don't know if you can see it, but it's right next to the coil here. And I'm going to set it to 5 volts. And then I'm going to attach one side to the positive and one side of the coil to the negative. And for our purposes right now, it doesn't really matter which side is which. And what we're going to do is lay it down on the page like this. And then we're going to do the same thing with this that we just did with the bar magnet. I'm going to take the compass, and then we're going to move the compass around. It's not plugged in yet, but we're going to map the magnetic fields around here. Notice that it's not plugged in right now, and the compass doesn't really move when I rotate it around. Not really. It doesn't really rotate very much around when I move the compass around because there's no current going through that coil. So for you, obviously you don't have this coil right here. So when you draw this in for your lab, just draw a coil that looks kind of like this. All right, so there's your coil. And now we're going to put the coil right there. And by the way, when I am attaching these leads to the coil, what I had to do, because there's insulation around the wire, I had to take some sandpaper. I took this sandpaper right here and I sanded off the insulation around the coil. So that exposed the bare copper wire here, and now I can make a good connection to it. So I'm going to make the connection. Actually, I need to set the voltage first. I'm going to turn it on. It says to set it to 5 volts. So I'm going to adjust it up to 5 volts. And then depending on the results we get at 5 volts, we could go a little bit higher than that. Maybe we could go up to 8 volts, 10 volts. We'll see. This would get pretty hot, though, if we left it exposed to a high voltage for a long period of time because it had a lot of current going through it. All right, so it's already getting slightly warm. All right, so here's our compass, and I'm going to do the same thing here. I'm going to all right. And if I needed to, I could crank up the voltage a little bit more. I'm going to unplug the coil so that I can crank up the voltage just a little bit more. It is a little bit warm. Not hot, but a little bit warm. I'm going to increase the voltage to 8 volts. All right, now I'm going to plug it in. You can see when I connected it, there was a little bit of a spark when I connected it. And now, when I rotate this around, you can definitely see the compass needle is definitely moving when I rotate this around. Even though this is a cheap little compass, it's not terribly accurate, but you can definitely see the magnetic field is having an effect on the orientation of this compass. Okay. All right, so that's probably adequate for what we need. It's still warm, it's not hot. That's good enough for what we need, so we can go ahead and disconnect this. And now what we're going to do is we're going to do the same thing that we did before with the previous one. So we want to draw the magnetic fields around this coil of wire. So it's going to look something there, kind of like that. So that is what the magnetic field around the what we call electromagnet. This is an electromagnet because we're using electricity to create a magnetic field. So we're still not quite done with this, but we're going to come back to this. And right now, I think I want to show you a couple of videos to demonstrate some of the same things that we're seeing right now. So we're starting to get a feel for what the shape of magnetic fields looks like. The next thing I want to do is share a couple of videos with you. They're all short. I've got 3 of them, but they're all less than a minute in length. So let me go ahead and share my screen with you. This first video is really meant for science teachers, and what they're going to do is they're going to put a clear plastic container lid over the top of this bar magnet and do pretty much what we did, except they're going to use iron filings or shavings and sprinkle that on top of the magnet instead of using a compass. But they're going to end up with something that looks pretty similar to what we ended up with.
Magnetic field all magnets create. Begin by placing the clear plastic or glass over a magnet. In this case, I use the cover of an old takeout tray. Carefully shake the iron filings out over the magnet and clear cover. You'll notice that as you shake, the filings will begin to arrange themselves almost magically across distinct lines.
It's magic.
This is a result of the north and south poles of each shavings arranging themselves with the magnetic field. When done shaking, make sure kids observe the pattern both overhead and from the side. From the side, they'll observe that the field is three-dimensional, meaning the magnetic field extends in all directions from the North Pole and wraps back around to the South Pole.
All right, that's actually a key distinction, is that the magnetic field is actually three-dimensional. And in our drawings, we could only draw it as two-dimensional, but it actually is three-dimensional. And there's another video that I want to show you that really helps to reinforce that point, that they are three-dimensional. This is the second video. What they've got here is a clear plastic hollow container that's filled with liquid, and that liquid has iron filings in it. And what they're going to do is they're going to place a bar magnet into a slot in the plastic piece. And what's going to happen is we're going to see the iron filings and the liquid around it arrange themselves into the shape of a magnetic field. So you can see the iron filings in the liquid. Now the bar magnet is going into the slot. And now you can start to see the shape of the magnetic field taking shape. All right, so I think you can really see that it is a three-dimensional shape when you look at it from this angle. This is probably my favorite video. This shows a whole bunch of compasses wrapped around this device, and they're going to take a bar magnet and they're going to put that bar magnet right in the middle of this device, and we'll see what happens to all the little compasses.
So we have around 270 little compasses attached to the field demonstrator. Now if we look at a bar magnet, this is a cylindrical bar magnet. You don't see too much. It's got a north and a south pole, but you don't see the magnetic field at all. But if you bring it up near the magnetic field demonstrator, you'll see that the little compass needles align themselves with the magnetic field lines. So let's see what the magnetic field lines look like around the whole bar magnet. Now the field demonstrator has a removable panel. You insert the magnet, slide the panel back in again. There we have it. The invisible is revealed.
The invisible is revealed. So I think you're starting to get a picture of what the shape of magnetic fields looks like, but there are a few more things that you need to keep in mind as you're drawing magnetic fields. So let's talk about that now. So when drawing magnetic fields, there are a couple of rules. The first rule for drawing magnetic fields is that the lines of what we call magnetic flux, these are the lines that we were drawing before in the lab. The lines of magnetic flux, sometimes you'll also see them called lines of magnetic force. Either one is correct. Lines of magnetic flux or lines of magnetic force never intersect. So as you're drawing magnetic fields, you should never have these lines that are going from the North Pole to the South Pole. They should never intersect. And the second rule, there's only two. The second rule for drawing lines of magnetic flux are that the lines of magnetic flux always go from the North Pole to the South Pole. And that seems kind of arbitrary and kind of silly right now, and maybe it was. At some point, this was arbitrary. But this is the convention now, and it has a significant impact on the way we're going to look at generators and motors later on. So it might seem arbitrary now, but this is a really important convention, and it has implications for the rest of the way that we look at electric machines. So we always need to make sure when we're drawing lines of magnetic flux, aka when we're drawing magnetic fields, we need to make sure that our lines of magnetic flux never intersect each other. And we also need to make sure that our lines of magnetic flux go from north to south. So how do you know if your lines of magnetic flux are going from north to south? Well, here's what we need to do. I told you that we weren't quite done with this lab yet. So go back to your lab. And what we need to do is draw some arrows on these lines of magnetic flux to indicate that they're going from north to south. So draw a couple of arrows on each line of magnetic flux. That's usually what I like to do. Okay, that's good. So now we see by all these arrows, we see that the lines of magnetic flux are going from the North Pole and then curving around in every direction on every side of the bar magnet. They're curving around and going towards the South Pole. On the second one here, it's not clear yet. We'll talk about this soon, but it's not clear yet which side of the electromagnet was the North Pole and which was the South Pole. So just to get in the practice of drawing these arrows, let's say that this was the North Pole and this was the South Pole. North Pole on the left, South Pole on the right, just for right now. And then let's go ahead and draw in our arrows so that they're going from the North Pole to the South Pole. Okay, good. So I want you to do that on your labs. Make sure that you have drawn in the arrows indicating that your lines of magnetic flux are going from the North Pole to the South Pole on number 1 and on number 2. I think I'm going to leave you to do number 3. There's just a little bit here. And what you want to do here is draw your lines of magnetic flux. And your lines of magnetic flux, remember, need to go from the North Pole, or poles, to the South Pole. And also, they cannot intersect. So clearly, you're going to have lines of magnetic flux going from this North Pole to this South Pole. And you're going to have lines going from this North Pole to this South Pole, and this North Pole to the South Pole. So there need to be lines of magnetic flux going from each of these three north poles to the south pole. Those lines can't intersect, and you need to make sure that you have arrows on those lines so that you show that the lines of magnetic flux are going from the North Pole to the South Pole. A few more things about magnetic fields that we need to talk about. First of all, let's say we want to show a stronger magnetic field. So let's say here is a bar magnet. And let's say this is the North Pole and this is the South Pole. And so I have my magnetic field coming around like this. Don't forget to draw your arrows. All right, now let's say I want to draw a stronger magnetic field. So I'm replacing this bar magnet with a stronger bar magnet. Stronger magnetic field is shown by denser lines of magnetic flux. Denser lines of magnetic flux. So if I replace this bar magnet with a stronger bar magnet, I could show this is a stronger magnetic field by having denser lines of magnetic flux. Like that, right? And I was careful not to let these intersect. They're not supposed to intersect, but I could draw more and denser lines of magnetic flux, and that would indicate a stronger magnetic field. The last thing I want to talk about in this video are the units related to magnetism, magnetic field strength and such. So let's say I have a magnetic field. This is my bar magnet. There's my magnetic field, and I want to measure the strength of the magnetic field at a certain point. Let's say we're going to measure the strength of the magnetic field right here, at that point right there. And there are instruments that you can use to measure the strength of the magnetic field. So the strength of the magnetic field, by the way, I may as well introduce the variable at this point in time too. The variable that we use to say the strength of the magnetic field, because we're not going to want to write this out, strength of magnetic field all the time, and we're not going to want to write out magnetic field all the time. The variable that we use to indicate the magnetic field is B. So the variable is B, and the strength of B, or the strength of the magnetic field, B, is given by units of Tesla, T-E-S-L-A, spelled just like the man or the car company. Most people are probably more familiar with the car company at this point. And we usually just abbreviate that capital T. All right, so the magnetic field is otherwise known as B. B indicates the magnetic field. The strength of B, which is the strength of the magnetic field, is given by units of Tesla, which are capital T. All right, so that's important to know. However, there's one other thing that we need to talk about right now. Oftentimes, we're not just interested in the strength of the magnetic field at this point. Oftentimes, you're going to see this when we talk about generators, we're not interested just in this point, but we're interested in, say, this area right here. So that's an area. Maybe there's a coil of wire right there. Right? That's actually what we're going to have in a generator. But let's say we've got a coil of wire, or for some reason we're interested in the magnetic field strength going through this area right there. So that's a different concept, and that is called magnetic flux. You can think about magnetic flux as the amount of the magnetic field going through that certain area. All right, flux in general, flux of anything, means the amount of something going through something else. Like I don't know if the movie Back to the Future is too old. I don't know how many of you have seen Back to the Future, but one of the famous things in that movie was the flux capacitor. That was an important part of the car in Back to the Future. No one really knows what a flux capacitor is, but it must have had something to do with something going through something else. Amount of current going through the capacitor or something like that. No one really knows, but flux means the amount of something going through something else. So magnetic flux means the amount of the magnetic field going through this certain area that we're interested in. All right. So the magnetic flux has a variable analogous to B for the magnetic field, but the magnetic flux variable is phi. Right? That is the capital Greek letter phi. I didn't invent these, by the way, so don't shoot the messenger. But magnetic flux is given by the variable phi, and the units is measured with units of Weber, W-E-B-E-R, and we abbreviate that capital W, lowercase b. All right. So the strength of the magnetic field at a certain point is given by Tesla, is measured by units of Tesla, and the magnetic flux, which is the amount of magnetic field going through a certain area, that's measured in units of Webers. All right. So there's a pretty easy relationship between these two, and that is to say that 1 Weber equals 1 Tesla times 1 meter squared. So if the average magnetic field in this area was 1 Tesla, and if this area represented 1 meter squared, which would be pretty big, but if this was 1 meter squared, then we could say that the magnetic flux through this area is 1 Weber. All right, so this is an important relationship. 1 Weber equals 1 Tesla times 1 meter squared. More generally, the equation that you're going to use over and over in the next month or so is the magnetic flux phi is equal to the magnetic field strength in that area, or specifically the average magnetic field strength in that area, times A, the area, where A is in meters squared. All right. So this relationship holds. Phi measured in Webers is equal to B measured in Tesla times the area, which is measured in meters squared. All right. So that's an important concept to understand because we're going to use that over and over in the next couple of weeks. Okay, I'm going to stop this video here because that's going to conclude our discussion of magnetism. That's really what we need to know in order to start to understand electric machines. So in the next video, we're going to start talking about electromagnetism. That is the relationship between electricity and magnetism. So I will see you in the next video.